Hello everyone. So from this video onwards, we will start building our fundamental to understand the Fourier series. So in this module, we will explore an alternative representation of signal and LTI system. So we will move on to alternative representation of signal and LTI system of signal and LTI systems. So earlier we have used a representation of signal as linear combination of a set of basic signal. Here we will use complex exponential as an alternative. So earlier we have seen that we have used impulse response to represent the signal. Now we will use some alternative representation, and that will be of the form of complex exponential. So and what it will result, so the resulting representation are known as continuous time and discrete time Fourier series and transform. So the resulting representation is called continuous time or discrete time Fourier series or transform. So in this video, we will focus on the representation of continuous time and discrete time periodic signal referred to as Fourier series. So this module is all about Fourier series. So now we'll discuss the response of an LTI system to a complex exponential. So this is very important topic that will bring you the fundamental for the Fourier series. So we will understand the response of LTI system, that is linear time invariant system, to complex exponential. So here the input is complex exponential, and we will see what is the response of the LTI system. So the importance of complex exponential in the study of LTI system, it emerges from the fact that the response of an LTI system to the complex exponential input is the same complex exponential with only a change in amplitude. So if we'll give an input to a system as complex exponential, we will get back the same input multiplied with some different complex variable that represent only the change in amplitude. So that is represented by, suppose for the continuous time case, so we are talking about the continuous time case, if we will give the input as e raised to the power st, we will get the output as h of s e raised to the power st. And for discrete time, suppose if we use the complex exponential as z raised to power n as input, the output what we will get hz z raised to the power n, z raised to the power n. So we are getting the same input back, only there is a variation in the amplitude, and these are the function of complex variable s or z. So hs and hz are function of the complex variable s or z. So now a signal for which the system output is a constant times input is referred to as an eigenfunction, and the amplitude factor is referred to as eigenvalue. So here we are talking about two important properties, that is eigenfunction and eigenvalues. And just to define, so a signal for which the system output is a constant times input is referred to as eigenfunction. So what is the definition? Definition says that a signal for which the system output is constant times input is referred to as eigenfunction. And the amplitude factor, so the amplitude factor is referred to as eigenvalues. So can you guess, like, from the previous expression, what is the eigenfunction and the eigenvalue? So yeah, the e raised to the power st factor here is your eigenfunction, and that amplitude factor h of s is your eigenvalue. Similarly, hz is your eigenvalue and z raised power n is your eigenfunction. So this is your eigenvalue and this is your eigenfunction. So now we'll just give a representation of like what is this constant amplitude factor and what is eigenvalue, eigenfunction. So now just for representation, consider an LTI system with impulse response of ht. So we have a LTI system whose impulse response is represented by h of t, and we are taking xt as e raised to the power s of t. And using the convolution property, what we can write yt as minus infinity to infinity h of tau x of t minus tau d tau. This is directly from the definition of convolution integral. And now we'll replace our xt by the expression which we have used. So this is our input xt. So we can write here as minus infinity to infinity h of tau e raised to the power s t minus tau d tau. Now we'll expand this, we'll write it as e raised to the power s t minus multiplied with e raised to the power of minus s tau. And as we can see that this is the integral which has a variable of tau. So e raised to the power st factor will be a constant for this integral. So which is like removed from this integral and it can be act as a constant. So it is multiplied directly to the integral as e raised to the power st multiplied it with integral minus infinity to infinity h of tau e raised to the power minus s tau d tau. And if we assume that, so there is an assumption here that this integral converges. So if this integral converges, so this is an assumption. So we have assumed to this integral to be converging. So how can we write this expression as? So we can write this expression as yt is equals to h of s e raised to the power st. And this h of s is your complex constant whose value depend on s. So this is complex constant whose value is depending on s. And what is this expression? H of s is given by minus infinity to infinity h of tau e raised to the power minus s tau d tau. So now we'll get an insight of what is this h of s function which we have already used in this expression directly. So this is the form of this h of s function. So this is the definition of that h of s function. So now this is your eigenvalue and this expression is your eigenfunction. So this is your eigenfunction. And I have already explained the definition of both of these. And similarly, we can like explain the same thing for discrete time case. So for the just for the like understanding perspective, for discrete time, if we take input xn as z raised power n, so yn will be from the definition of your convolutional integral or summation k is equals to minus infinity to infinity h of k x of n minus k. And now again we'll replace x of n as z raised power n. What we'll get summation k is equals to minus infinity to infinity h of k z raised to the power n minus k, and again z raised to power n is a constant for this summation, so it will be put out of this summation, and we can write it as z raised to power n multiplied with summation of k varying from minus infinity to infinity h of k z raised to power minus k. So again, if this expression converges, we can write it in compact form as yn is equals to h of z raised to power n, and where here z is a function which depends on z, and hz can be represented as summation k is equals to minus infinity to infinity h of k z raised to power minus k. So again, as per the definition, this is your eigenfunction and this is your eigenvalue, and this is for discrete time case, and they are very analogous to that of the continuous time case. So this is your eigenvalue. So why we are interested in eigenfunction? We can like have an insight of this by having an example. So suppose we have input represented by xt is equals to a1 e raised to the power s1t plus a2 e raised to the power s2t plus a3 e raised to the power s3t. So by the understanding of eigenvalue and eigenfunction, what we can do, we can directly write the output of this kind of input. So we can using the property, using eigenfunction property which we have discussed recently, we can write all the outputs directly. So a1 e raised to power s1t will give an output corresponding to a1 h of s1 e raised to the power s1t, and a2 e raised to the power s2t will give an output equivalent to a2 h of s2 e raised to the power s2t. Similarly, a3 e raised to the power s3t will give an output corresponding to a3 h of s3 e raised to the power s3t, and the output will be directly the summation of these two because of the superposition principle. So from superposition principle, what we can write? We can write yt as a1 h of s1 e raised to the power s1t plus a2 h of s2 e raised to the power s2t plus a3 h of s3 e raised to the power s3t. So this is the advantage of having this eigenvalue property, eigenvalue eigenfunction property, and we can write the output directly. So this is all about the eigenvalue and eigenfunctions. So now we will discuss about the linear combination of harmonically related complex exponential. So now in this module we will discuss about linear combination harmonically related complex exponential. And that will finally lead to your expression of Fourier series. So for a periodic signal, we know that by definition that xt, if a signal is periodic, then xt will be x of t plus capital T for all value of t, and the fundamental period of xt is the minimum positive non-zero value of t for which this expression is satisfied. So the fundamental period is the minimum positive non-zero value, minimum positive non-zero value for which this expression is satisfied, and consequently the omega naught, that is fundamental frequency, will be given by 2 pi by t. This we already discussed in the part of periodic and non-periodic signal in the previous video. And suppose we have taken a periodic signal, and we have also discussed about the complex exponential. It is a periodic function with fundamental frequency of omega naught and fundamental period of 2 pi by omega naught. So suppose we take a complex exponential, that is e raised to power j omega naught t. So this is your periodic complex exponential. Here omega naught is your fundamental frequency, and 2 pi by omega naught is represented as fundamental period. Now we will represent phi k t as e raised to the power j k omega naught t. Here k will vary from 0, plus minus 1, plus minus 2, and so on. So what this phi k represent? It represents harmonically related complex exponential. So harmonically, that varying the value of k will generate different harmonics. So this represent harmonically related complex exponential. Thus, a linear combination of these kind of harmonically related exponential series can be represented as, so xt can be represented as your summation k is equals to minus infinity to infinity ak e raised to the power j k omega naught t, and consequently this can be written as k is equals to minus infinity to infinity ak e raised to the power j k 2 pi by t multiplied with by t, and this is the expression for your Fourier series. So Fourier series of any signal x of t can be represented in terms of the linear combination of harmonically related complex exponential, and this is also will be the periodic signal, and the period is again capital T. So this can be directly understandable by that if we put k is equals to 0, we will get a constant term. So if you put k is equals to 0, we will get a constant term. If k will be equal to plus minus 1, it will be the first harmonic with the frequency of omega naught. If k is equals to plus minus 2, we will get the second harmonic with the frequency as 2 omega naught, and so on. So next we'll see an example like how to build a function from its harmonic component, and like that will lead to some insights of the discussion we have done so far. So what we'll do, we'll take an xt signal with fundamental frequency of 2 pi. So the fundamental of 2 pi. So xt, from the representation earlier, we can use some k value which will vary from minus 3 to 3 ak e raised to the power j k 2 pi t, and now we take some value of a naught as 1, a of 1 is equals to a of minus n is equals to 1 by 4, a2 will be equal to a of minus 2, that will be equal to 1 by 2, and a3 will be equal to a of minus 3, and that will be a value of 1 by 3. So we have taken some values of the coefficients, and when we write xt 1 plus 1 by 4 e raised to the power j 2 pi t plus e raised to the power minus j 2 pi t. Similarly, we can write the other coefficients 1 by 2 and the corresponding frequency terms plus e raised to the power, so it will be 4 minus j 4 pi t, and similarly for 1 by 3 e raised to the power j 6 pi t plus e raised to the power minus j 6 pi t. And from Euler's formula we can write it as 1 plus 1 by 2 cos 2 pi t plus cos 4 pi t plus 2 by 3 cos of 6 pi t. So this is the signal we will get, and that is the derived from the complex exponential sum, which is having these coefficient values and the fundamental period of 2 pi. So this is just a representation like how a signal is built up using your complex exponential. Now we will derive a formula for the coefficients, like how to get the coefficients out of your signal. To represent a signal, how we will get the coefficient values. So we have given the expression for Fourier series as xt is equals to k varying from minus infinity to infinity ak e raised to the power jk omega naught t. Now what we will do, we will multiply both sides with some value e raised to the power j n omega naught t multiply with x of t, and this will be equal to summation k is equals to minus infinity to infinity ak e raised to the power j k omega naught t multiplied with e raised to the power minus j n omega naught t. So the factor of e raised to the power minus j n omega naught t is multiplied on both the side. Now we'll integrate both sides from 0 to t, that t is equals to 2 pi by omega naught. So now integrating both sides from 0 to t, where t is given by 2 pi by omega naught. So what will be the expression? So this expression will be changed to 0 to t integration of xt into e raised to the power minus j n omega naught t dt, that will be equal to 0 to t summation k is equals to minus infinity to infinity ak e raised to the power j k omega naught t e raised to the power minus j n omega naught t dt. So now, summation and integration is linear property, so we can interchange them. So here what we can write, it will be 0 to t x of t e raised to the power minus j n omega naught t dt should be equal to summation k is equals to minus infinity to infinity ak. So integration is now shifted to this expression e raised to the power j k minus n omega naught t dt. Now this function has a special values, so this can be represented by, this integral can be represented at 0 to t e raised to the power j k minus n omega naught t dt. And if we'll put k is equals to n, then what we'll get? We'll get a value of t. So it will be t for k is equals to n, and it will be 0 for k is equals not equal to n. So to put it as 0, we can just expand it in the Euler's form as cos of k minus n omega naught t and sine of that function, and if we'll integrate sine and cos in its period, then it will be 0. So that satisfies this condition, that when k is not equals to 0, it will be integration of sine and cos in its period, so that will be an 0 value. So now we'll put this value in this integration. So what we'll get, for a value of n only we'll get this expression. So rearranging, what we'll get a n is equals to 1 upon t 0 to t x of t e raised to the power minus j n omega naught t dt. So this is the expression for coefficients. Using this expression, we can get the coefficients out of it. So these are the coefficients. So to conclude this module, what we have learned, we learned the pair of equations defining Fourier series for continuous time signal as, we will write xt as summation k is equals to minus infinity to infinity ak e raised to the power j k omega naught t, and the coefficient values can be deduced from this expression, which shows that 1 upon t integration over the period xt e raised to the power j k omega naught t dt. So these two formulas are important to in the case of Fourier series, and we'll see some examples and some questions also to get how Fourier series and Fourier coefficients are computed. So thank you.